Okay, bloggers, time for more probability notes. And today we are looking at the addition law. So I briefly mentioned this in probability notes number 1, but now we're going to get a little bit more in depth into it. And I just realized I misplaced my pencil. Great. Going to have to go with a backup pencil. Too bad. All right, so here we have this equation. We've been messing around with Venn diagrams in my classes. Mr. Myers' class, you guys haven't seen the Venn diagrams so much, but hopefully you can follow along anyway. You'll get a chance to practice with Venn diagrams on Monday. So what we have is we have two events, A and B, and the probability of A or B happening, so you have had the notes on and or, so this is an or problem. The probability of A or B happening, you can summarize it like this. It's equal to the probability of A plus the probability of B minus the probability of their overlap. Okay, so here it is put another way. The probability of either A or B or both happening, so all instances of A or B, is equal to the probability of A plus the probability of B minus the probability of both of those things happening. Okay, so what does this mean? This formula is saying that if you want to count the number of ways of getting A or B, count the number of ways of getting A, add to that the number of ways of getting B. However, the number of ways of getting A and B will have been counted twice, so we need to compensate by subtracting it. We need to subtract the overlap. So you can see that visually here. If this is A, event A, and this is event B right here, if there is some overlap here, this is not the same as adding all of A plus all of B. Because if you look at the area here, the area of A overlapping with B is a smaller area than adding all of A plus all of B. Okay, this is a smaller area than this. This is more area. So these two things are not equal. Okay, so when we talk about this is also called the union. When we talk about the union, let me write that in here. Boy, I really don't like this pencil. If we talk about the union of A and B, what we're talking about is all of A and all of B. We want all of this, so we can think of that as an area. But that's not the same as just taking all of A and adding all of B if there's some overlap. So if there's some overlap, what's really happening is it's like having all of the area of A and then having the area of B, but with a bite taken out of it. So you can see if I cover this part up right here, this oval is all of A, but B looks more like this. Okay, so here's my B, here's my A. So it's all of A, but not quite all of B, because I've already counted this part in with the A part. So these two things are equivalent. These are not. So how do we get this part here? How do we get rid of that from the B? Well, that's the overlap. That's this part right here. So what I want to do is I want to take all of A and then all of B, but subtract this overlapping part. So this part right here is the same as this part right here. It's the overlapping part. So this is the intersection of A and B. Okay, we call that the intersection of A and B. Right, so this shape right here is B minus that intersection. Okay, so that bite taken out of it, that's minus that intersection, minus the intersection of A and B. Okay, so if I want the union of both of these, so if I want the union, I want all of this. Okay, so if I actually want all of this, it's going to be all of A plus all of B, but then we're going to subtract off that intersection. So you can really see that right here. Again, all of A, all of B except minus that intersection part. Okay, and there it is. I moved it over to here. All right, so how do we write that? With our set notation, okay, our probability notation. So the probability of getting A or B, so remember this means or, it's also called a union. Okay, so the official technical name is the union of A and B, but when we see probability questions, it shows up as the word or. We're going to take the probability of the first event plus the probability of the second event minus the probability of, and this is called the intersection of A and B, intersection. And in probability problems, that shows up with the word and. It needs to be A and B at the same time. Okay? So we are going to do an example of this. So when I handed you the sheets of paper, I changed my mind in the order that I wanted to do things in. So sorry about that. I'm going to talk about mutually exclusive a little bit later. So right now we're just going to do an example using this formula. So here's the example. We're going to roll a die, find the probability of getting a multiple of 2 or 3. So we actually did this previously in the notes, but now we're going to do it formally using this equation. So event A, okay, so event A, this part right here, is going to be rolling a multiple of 2. So on a die, we have the numbers 1 through 6. So the probability of rolling a multiple of 2, well, what are my multiples of 2? There are 2, 4, and 6. So I have 3 possible ways of rolling a multiple of 2. Okay, event B is rolling a multiple of 3. So on a die, my multiples of 3 are 3 and 6. So there's 2 ways I can roll a multiple of 3. But notice there's one of these outcomes that they have in common. So they both have a 6, so there is overlap. We have overlap in this situation. Okay, so if we were to actually draw like a Venn diagram of this, we would see that we actually had some overlap. So we could draw a little Venn diagram. Event A would be these 3 things, 2, 4, and 6. So 2, 4, and 6. And then event B also has a 6 and a 3. And then there is the entire sample set, the things that are neither of those. So the things that are neither multiples of 2 or multiples of 3 would be the other numbers, 1 and 5. Okay, so we could draw this as a Venn diagram as well. Okay, so there is one outcome that is common to both A and B, okay, and that is the number 6. So now we're going to use our formula. Okay, we're going to go ahead and find our formula. So in order to do our formula, the probability of A is the probability of a multiple of 2, and we said that's 3 out of 6 because there's 6 sides to a die. Then the probability of B would be 2 out of 6 because there's the numbers 3 and 6 out of 6 numbers on a die. And the probability of getting both of those at the same time, a multiple of 2 and a multiple of 3, getting both of them, getting an and situation, it's a multiple of 2 and a multiple of 3, is 1 out of 6, because that's the overlap, the 6. Okay? So the probability of the union of getting both of these is I'm going to take my probability of A, here's my probability of A, plus my probability of B, minus the probability of the overlap. And that gives, so 3 plus 2 is 5, minus 1 is 4, gives me 4 out of 6. So the probability of getting a multiple of 2 or 3 is 4 out of 6. Okay, and you can see that on here as well. If we talk about the union of A and B, the union of A and B is all of these, everything that's inside those 2 circles of event A and event B. And notice how many outcomes are there. There's 1, 2, 3, 4 outcomes. And then in the entire sample set, there is 1, 2, 3, 4, 5, 6. So 4 that meet our criteria, and a total of 6 outcomes altogether. Okay, so this is an example of using the formula. Sometimes it's way easier to just draw the Venn diagram or just think through the problem than it is to use the formula, but sometimes the formula is actually quite useful. So it's good to know how to do things several different ways. Okay, next thing I want to talk about is what if there hadn't been any overlap? What if I was talking about a situation where event A and event B could never occur at the same time? Then what do we do? Okay, so that is called mutually exclusive events. So if there's no possibility of A and B occurring at the same time, then the intersection of A and B is going to be 0. There's nothing. They have nothing in common, then the intersection is going to be 0. So these events are said to be mutually exclusive. Notice how big I made this word. This is a very important word, mutually exclusive. They cannot happen at the same time. They cannot happen simultaneously. So in this case, the formula reduces to the probability of A or B, okay, the union of A and B, or saying it like it would be in a probability problem, the probability of A or B, it's just going to reduce down to the probability of A plus the probability of B, because minus the intersection, well, if the intersection is 0, well then obviously there's nothing to subtract. And here's an example of that happening. What is the probability of rolling a 2 or a 5 on a die? Well, the probability of rolling a 2 is 1 out of 6, and the probability of rolling a 5 is also 1 out of 6. And it is not possible to roll a 2 and a 5 simultaneously. You can't do it. Okay? If I roll one die, I can't, only one number is going to come up. These events are mutually exclusive. They cannot happen at the same time. So therefore, the intersection of those two things happening is 0. It's impossible for them to happen at the same time. So therefore, the probability of the union of rolling a 2 or a 5 is the probability of the 2 plus the probability of rolling the 5, which gives us 2 out of 6. So rolling a 2 and a 5 in one roll are mutually exclusive events. Cannot happen. In that case, it's a very simple calculation. You just add the two separate probabilities together. You don't have to worry about overlap. So in their Venn diagram, if I were to draw a Venn diagram of that, you would have event A and you would have event B, and they would not be overlapping. And then you'd have your universal set like this. So I'd have a 2 here, I'd have a 5 here, and then all the other numbers would be out and about. 1, 3, 4, and 6. They'd be out floating around in the universal set. So how many ways can I win? 2 ways I can win out of how many possibilities? 6 possibilities. Okay, so here it is with the Venn diagram, and here it is with the equation. All right, we've got a couple of examples to work through. So we're going to go ahead and use the formula on this. We're also going to learn how to use Venn diagrams, but we're going to do that some other time. So we're just going to work through this example. So here I've got a fruit pie, and when a fruit pie is selected at random, the probability it contains pears is 1 out of 5. The probability it contains apples is 1 out of 4. And 10% of the pies contain both apples and pears. So what is the probability that a random selected pie contains apples or pears? Okay, so we want the probability of apples or pears. So I'm going to use A is going to be my apples, and P is going to be my pears. So I want the probability of A, or that would be union P. That's what I'm trying to find. Okay, so it's going to be equal to the probability of A, apples, plus the probability of P, pears, minus the probability of both of those things happening, the intersection of apples and pears. So let's go ahead and fill in what we got. Do we know the probability of apples? Probability it contains apples is 1/4. The probability that it contains pears is 1/5. And the overlap, it says 10% of the pies contain both apples and pears. So I need to minus 10%. So 10%, I want to write it as a fraction. So 10% is the same as 10 over 100. That's what a percent means out of 100. And that reduces to 1/10. So I'm going to put in minus 1/10. And that is going to give me my probability of A or P, getting apple or pear. All right, so I need to rewrite these with common denominators. So this would be, I'm going to change them to add a 20. I can change all of these to a denominator of 20. So 4 goes in 25 times, so 5 times 1 is 5. 5/20ths is 1/4. 5 goes into 24 times, 4 times 1 is 4. 10 goes into 22, 2 times 1 is 2. Okay, so now my probability is going to be 5 plus 4 is 9, minus 2 is 7. So my probability of selecting apples or pears is 7 out of 20, and I can change that to a percent, and that happens to equal exactly 35%. So I have a 35% chance of getting a randomly selected pie contains apples or pears, okay? Because there is some overlap. There are some pies that contain both, so I had to subtract that off. I couldn't just add the probability of pears and the probability of apples. Okay, the next problem I gave you, I've actually kind of like hemmed and hawed whether I should give this to you because I think it's actually really strangely written. So I think what it's trying to say, I have a feeling this 25% of the students in a school play football or tennis. I think that's erroneous information, extra information. We actually don't need that information. Zoom in a little bit here. I don't think we need that information because these other numbers don't make sense. It says the probability of randomly chosen student playing football is 3 out of 5. That would mean that 60% of the students play football. But it says only 25% of the students in a school play football or tennis. And they're saying that 60% of the students at a school play football alone. So I don't think we want this information. I think the way that this question is being asked is if we select a person who plays football or tennis, then the chance that they play football is 3/5, and the chance that they play tennis is 5 out of 8. I think that makes more sense. So if we already know that this person plays football or tennis, then there's a 3 out of 5 chance that it's football that they play, and there's a 5 out of 8 chance that there is tennis that they play. So, and then it says what percentage of the students play both football and tennis. Okay, so I'm assuming that that this question is written incorrectly. And so the way that this would work out is I have my probability of football is equal to 3/5, and my probability of tennis is equal to 5/8, and the probability that they play both is what I'm trying to find. So what I'm thinking, though, is there's no way that we're talking about a 25% chance of selecting somebody who plays football or tennis when there's already a 60% chance of selecting somebody who plays football. It doesn't make any sense. So what I think is we're going to be talking about of all the students who play football or tennis, so that's all the students. So the probability of football or tennis is going to be 1. It's going to be everybody. Okay, so I think that's an assumption that we have to make for this problem because otherwise it really doesn't make any sense to me. So the assumption here is we're only talking about students that we already know play football or tennis. So basically we're getting rid of this thing about 25% of the students in the school. We're just going to say we've already selected a student who likes football or tennis. What's the probability that they like both? Okay, so we know the union's going to be 1. So the union's going to be 1. So the probability of football union with tennis is going to be equal to the probability of just football plus the probability of just tennis minus the probability of football and tennis. And this is what we're trying to solve for, football and tennis. So let's fill in what we know. We're going to make this assumption that the person already plays either football or tennis, so that's 1. The probability of football is 3/5. The probability of tennis is 5/8. And we're trying to find this, so I'm going to call that X. We're solving for X. Okay, the probability of football and tennis is going to be X. All right, so let's go ahead and get a common denominator here. 5 and 8, I can make them both equal to 40. So 5 times 8 is 40, so that would be 24 over 40. 8 times 5 is 40, so 5 times 5 is 25. And when we add these probabilities together, notice what happens. It equals more than 1. We get 49 out of 40 is equal to 1 whole. Okay, we could also write that as 40 over 40. Oops, sorry, you can't see what I'm writing. Okay, so we can also write that 1 whole is 40 over 40 is equal to 49 over 40. Oops, I'm sorry, that should have been a minus sign. Problem with having 10. Minus x. All right, I'm going to add x to this side so it becomes positive, and I'm going to subtract my 40 over 40. So I have 49 over 40 minus 40 over 40, and I'm left with the probability that they play both would be 9 out of 40, and I change that to a percent. That equals 22.5%. So there's a 22.5% chance that A randomly selected student who plays one of these sports actually plays both of them. So 22.5% of those students who play tennis or football actually play both. Okay, so 25.2% play both football and tennis. Okay, and that would be of students who play either of them. Okay, so I had to kind of reinterpret the question there because it didn't make sense. If only 25% of the students in the school play either one of those, how can 60% of the students in the school play just football? Didn't make sense. So there's the question, having to interpret that question or that 25% thing a little bit different. All right, that's it. I am done. Hey, shout out to Jaden and Izzy. Hope you enjoyed my notes. Bye.